Okay, so go ahead and pause the video and see if you can find the area bounded between these two curves. And just as a hint, try to find the answer by integrating with respect to x, and also try the other method of integrating with respect to y and see what you get in each case. And see if you understand why you get what you get in each case. So go ahead and pause and see if you can figure that out. So here's the answer. And by the way, this answer, you should get this whether you integrate with respect to x or whether you integrate with respect to y. And that's kind of a key insight when you're finding the area bounded between curves. It actually doesn't matter. If you set things up correctly and do the problem correctly, you should get the same answer in both cases. So whichever way you did, you should get 1/6 for this one. If you got it right and everything feels easy, feel free to skip this video. Otherwise, stick around and we'll dive into the explanation. Okay, first, let's start off by integrating with respect to x. So if we're integrating with respect to x, x is our input, so we need to rearrange the function so that x is the input, and that's already done for us. So we're already good on that front. Now what we need to do, which is the first part of all of these, is to actually find the bounds of the integral. Now, in some cases, in some problems, they'll actually tell you, like between x equals whatever and x equals some other bound. They'll actually tell you the bounds. Here they do not. When they do not, generally what that means is that the curves that they provide will intersect somewhere, and those intersection points will be the bounds. So first, we need to find those intersection points. And you can do that just by setting these equal to each other. So set the x plus 1 and the x squared plus 1 equal to each other, and then solve for this. Now, the way you actually solve this is a quadratic, first off. So the way I'll do this, I'm basically going to subtract this to get everything on the other side. So I'll get 0 equals x squared minus x, and then 1 minus 1 will be 0. So I just end up with this. And then if I solve this quadratic, so to speak, factor out an x, I get x minus 1, and I get 0 equals x times x minus 1. So what does this mean? This means that the zeros are x equals 0 and then x equals 1. So there you go. At x equals 0 and at x equals 1, those are the intersection points. So that's half of the battle. Now, the next thing we need to understand, remember the equation that we're going to use for all of these, actually let me pull these back down, but if these are our two intersection points between x equals 0 and x equals 1, and these are our equations, we're always going to use the formula, basically the integral between a and b of f of x minus g of x. And now why is this formula true? Again, this is not really a concept video. This is just showing how to work these problems. I explain this conceptually in another video, but for now, we'll just take it for granted. But this is basically the area between the curves. And f is always the upper function, and g is always the lower function. So if you can identify which function is the upper and which one's the lower, you can just plug them into this formula. So how do you do that? Basically, you need to create kind of a modified version of a sign chart. It's more like a greater than or less than chart. But basically, the idea is we already know that they're the same at x equals 0 and at x equals 1. So at x equals 0 and at x equals 1, and actually let me rearrange this. So 0 and then 1. So at these values, we already know that they're the same. So we already know that, and actually let me create a little bit more room. So we already know that f of x equals g of x. That's kind of the whole point of what we just did above. Those are the intersection points. And if you're not sure about that, check it. So plug in x equals 0. Y equals 1 here. Y equals 1 here. So yeah, they are equal. And then plug in x equals 1. Y equals 2 here. Y also equals 2 here. So in both of these cases, at the intersection points, we already know they're equal. What we really care about is between those two bounds, between those two intersection points, which one's greater than the other. So that's the idea. So we can pick any value, and the easiest one probably is to pick 1/2. So basically, just pick 1/2 into this function. And by the way, I'm calling it f of x. I'm calling this the first one. I should probably call this. Yeah, I'll just call this f of x just to keep it easy. Actually, that can be confusing with how I've defined this over there. But we know that they're both equal. And actually, hold off. We'll actually figure out which one's the greater one, and we'll call that f of x. So here, for this first one, maybe I'll call it y1 and y2, just for now. So if I plug that in, hopefully it makes sense that y1 evaluated at 1/2 is what? What is that going to be? It's going to be 1 plus 1/2, so 3/2, 1.5, so 3/2. And then y2, we can do a similar thing. So what would happen if we evaluate that function at 1/2? Well, 1/2 squared is 1/4, plus 1 is 1 and 1/4, or 5/4. 5/4. So which one of these is bigger? Actually, y1 is bigger. So y1 is actually bigger than y2. Now again, according to this logic, and I won't go through the logic here, or actually I will, I'll go through it briefly. But basically, if y1 is greater than y2, greater than or equal to, I should say, y2 at one value in between x equals 0 and x equals 1, then it must be greater than then y1 must be greater for all values between 0 and 1. Why is that? Well, think about it. We're dealing with polynomials here, so these functions are already continuous, which means they can't teleport. So for example, if we have, hypothetically, if we have one function down here, so let's pretend we're looking at a graph like this. So let's pretend we have two different graphs, and these are the intersection points. We already know that they have to be continuous. So we can't just go along here and just kind of have a discontinuity and just break and come down here. Now, if your functions are not continuous, then that could happen. So you have to watch out for that. This logic only works if these are continuous functions, but these are polynomials, so they are. So they're continuous everywhere. So we can't do that. In order for this function, if at this point the black one really is above the red one, in order for that to not be true, they need to cross, basically. In other words, there needs to be another intersection point so that the black one can dip below the red one. And we already know that can't happen because we found the only two intersection points, 0 and 1. So if we know that x equals 0 and x equals 1 are the only intersection points, the only possible points where the curves can swap, which one's the upper and which one's the lower. And by the way, they don't have to swap. One thing that could happen, the black one, instead of going through at the intersection point, it could bounce back. That is theoretically possible. So just because they have an intersection point doesn't guarantee that they're going to swap. It just means they could, and you have to actually check that. But if there is no intersection point and the functions are continuous, that's a big caveat, then that actually is a guarantee that they can't swap. So that's why we only have to check one point, like this 1/2. If we can tell that one function is bigger than the other function at a certain x value, and the functions are continuous, that same function has to be bigger than the other one for all values in between the two bounds. So that's the kind of logic we can use. And again, we still have no idea what these curves look like. I mean, you could graph these by hand if you wanted, but the key point when you're dealing with problems like this is that you don't have to. You can solve this entire problem without ever knowing what the graphs actually look like, and that's actually a good skill to build. So in other words, which one's the bit greater one on this interval? Y equals x plus 1. So hopefully that makes sense. Now, if we pop this in, let's pop this into the integral using this equation. It's going to be the integral from 0 to 1 of what's the upper function, x plus 1. So let's say x plus 1 minus x squared plus 1, because that's the lower. And there you go. If we evaluate this, I'll do this quickly. So the 1's kind of go away, but we have x minus x squared, integral of that from 0 to 1. If we integrate this, what do we get? 1/2 x squared minus 1/3 x cubed. And if we evaluate this, so that's just the antiderivative, evaluate that between 0 and 1. Hopefully it makes sense that we get 1/2 minus 1/3. If we find a common denominator, we can say 1/2 is 3/6, and then 1/3 is 2/6. 3/6 minus 2/6 is 1/6. So there you go. That's kind of the idea. And now let me pull up another visual so that we can kind of show what this actually looks like. Okay, so looking at this one, you can see that this right here, this is the line x plus 1, the blue one, and you can see it really is greater, although slightly, for that interval. And again, we're intersecting at x equals 0, x equals 1. And then this one underneath, that's basically x squared plus 1, which is actually the lower curve. So you can see that if we subtract 1 from the other throughout the whole way, then we're good. So that's what we get. 1/6 apparently is this green area if we're thinking about, integrating from top to bottom. If we're integrating these like line segments, f of x minus g of x at each point to get that length. If we integrate all of those, we get the area. So there you go. Hopefully that makes sense. Now let's talk about how to do this when integrating with respect to y. Now, basically, the way we're going to do this when we integrate with respect to y, it's the same area that we're talking about, but our independent variable is now y. So instead of going up and down, the biggest thing that's going to change is that we're going to be going left to right. So the line segments, so to speak, that we're going to be integrating or adding up are now going to go left to right or right to left rather than up and down. So that's the idea. Now, one thing we have to do here is remember, if this is a function of y, we need to get that as the independent variable. So basically isolate x, in other words, for each of these. So if I isolate that, hopefully it makes sense. For this first one, I get x equals y minus 1. And then over here, I get x equals plus or minus the square root of y minus 1. Now, in this case, hopefully it makes sense that all the y values are positive in this case, whereas they don't have, or they don't, or I should say all the x values are positive in this case. They don't have to be. Like if we went over here, that would be like the negative half. But if we're just talking about this, that would be the positive half. So that's what we're talking about here. So there we go. Here are two functions, and we can kind of already tell which one, and by the way, I should mention, we don't care in this case about which one's the top and which one's the bottom. Here we care about which one is the rightmost and which one is the leftmost. And the reason for that, by the way, is because when we're dealing with our equation, integral of f of x minus g of x, oftentimes people will say that f of x, and even I said it previously, that f of x is the upper and g of x is the lower function. That's actually not true. It's that f of x is the largest function, largest output, and g of x is the smallest output. It just so happens that when y is our output variable, the largest output means the upper, and the lowest output means the lower. But when x is our output, as it is right now, of the largest output, largest x value actually means the most to the right, and the other one means the most to the left. So just by looking at this, hopefully you can tell that the square root of y minus 1, the red one, is actually the rightmost function. So I'm predicting that this is going to be the upper. But we need to check that. So how do we do this? We still need to figure out the intersection points. Now we can see visually, like looking, what the intersection points are. Apparently it's 0, 1, and then 1, 2. So in the previous example, when we were integrating with respect to x, we were integrating between x equals 0 and x equals 1. Those were the x coordinates of the intersection points because we were dealing with x as the input variable and integrating with respect to x. Here, because we're integrating with respect to y is the input variable. We need to find the y coordinates of the intersection points. So we can see that visually here, but even if we couldn't see it, we don't need to actually see this to figure this problem out. We could find it numerically just like we did before. How would we do that? Basically set these equal to one another. So set these equal to one another and solve. So if we try to solve this, how would we do it? This is essentially a radical equation, so you'd have to square both sides to start. And I'll go through this. This is like kind of some basic algebra. And then what do we get? Y squared minus 2y plus 1 equals y minus 1. And then I'll add the 2 and I'll subtract the y. So I get y squared minus 3y plus 2 equals 0. So there you go. If you think about this, now we need to factor. What do we get? We get y minus 3, and we get, or sorry, not minus 3, minus 2, and then y minus 1 equals 0. So we get y equals 1, y equals 0. Or sorry, not 0, y equals 1, y equals 2. Now, one thing I will point out is that there's a possibility of creating extraneous solutions on this step. When we square both sides, we might introduce extraneous solutions. So we need to take the solutions we got. And again, this was not true in the previous case. This is an algebra thing. But whenever you have a radical equation that you're solving, which we do here because there's a square root involved, and you square both sides, whenever you do that step, you might be introducing solutions that aren't, they're solutions like to the later problem after squaring, but they actually aren't solutions before squaring. So we need to double check, I guess is what I'm saying. Now let's actually check that. So the way we check that is take each of these and plug them into the original equation. So if I plug y into this, I get 0 equals square root of 0. So that's actually not extraneous. This is actually good. And then we can try the same thing with 2. That's actually also good. So we're in a special case where both of these are actually good. So neither of these are extraneous. So that's not a concern. But basically, these are going to be the balance. And again, we can already see that visually, right? Y equals 1 to y equals 2. So the way we're going to look at this now is, for a certain y value, we're going to try to figure out an equation that tells us the length of this line segment as a function of y. And again, that's just the rightmost minus the leftmost. So if these are the two functions and these are the bounds, we can, again, kind of like we did last time, figure this out. So if we're going between 1 and 2 as our bounds, and then these, let me pull these down, and these are our two functions, then we can, and I'll do this kind of like we did before. I'll call this, x1 and call that x2. We can basically test these out and see, we can see which one, or basically which one is greater than the other in between. So let's actually do that. So here, we already know they're equal here. So f of x equals g of x because of their intersection points. Actually, it's got to be with y, sorry. G of y, because now y is our input variable. So f of y is less than g of y. But now we need to test some value in between. What's the easiest value? Probably 3/2, 1.5 is the clearest value. And now let's try that. So for x1, what would that equal? 3/2 minus 1, that would equal, so x1 evaluated at 3/2 would be 1/2. And then x2, what would that be? That would be, or evaluated at 3/2, that would be the square root of 1/2. And this might be confusing. Which one of these would be greater? You can think of it like this, like we have 1/2. So over here we have, for x1 and then x2. Here we have just 1/2. Here we have, if you think about it, if you apply the square root, 1 over square root of 2. And now first off, you could just pop these into a calculator and see which number is bigger. The second option that you have is to think about it logically, but it's a little trickier. So here, the numerators are the same, so that's fine. The only thing that's different is the denominators. Now, which one of these numbers is bigger in the denominator? Hopefully it makes sense that 2 is bigger than square root of 2. And if you don't believe that, square both of them and see. If you square both of these, this would become 2 and this would become 4, and 4 is definitely bigger than 2. So if the square of the left is bigger, then the original left was bigger as well. That's one way to think about it. So we've done that. Now what happens is, or what needs to happen, is we need to essentially, how should I word this? Or here's the logic, I guess. If this denominator is bigger than that denominator, then this number is smaller than that number. So this number has to actually be bigger. So x2 is actually bigger, which means that this function, this one is f of y, and this one is g of y, which, by the way, that's what we said at the very beginning. That's what we predicted just by looking. We could tell that that's the rightmost curve. But here you can tell, this is how you can tell numerically without having to visualize anything at all. The red one, which is square root of y minus 1, that is the rightmost function across the entire interval. So there we go. Once we have that, we can now integrate. So we're going to integrate this time from y equals 1 to y equals 2, integrate with respect to y. And it's like we're going to add all of these y values up all the way. And at each y value, we're going to add a new line segment, basically. And then add those all up to see what the total area is. So this will be what? This will be square root of y minus 1 minus y minus 1. And then we can integrate that. So this is going to be, it looks like a little bit more difficult than the last one, but we can still do this no problem. So if we try to take the antiderivative, this is I'm kind of doing a little bit of u sub in my head, but it's a relatively easy version of u sub. So try that, and if you want to double check that this works, quickly take the derivative to see if that gives the right answer. So I just did the inverse power rule. The derivative of the inside is 1, so that's not really a problem chain rule wise, or u sub wise, I should say. But yeah, if you check this, that is the correct antiderivative. And then for this one, it would be minus 1/2 y squared, and then plus y, because that would be plus 1, and the antiderivative of that is y. And then we're integrating that between 2 and 1. So let's think about how this would play out. So first off, it would be what? 2/3 times 2 minus 1. So 2 minus 1 to the 3/2. And that's going to simplify to 1, so the 3/2 doesn't matter anyway. Then minus 1/2 2 squared plus 2. So that's if we evaluate the antiderivative at 2. And then if we evaluate everything at 1, let's see how that turns out. So 2/3, 1 minus 1, so that'll become 0. That doesn't matter. Minus 1/2, 0. So here, well, not 0, that'll be 1 actually. 1 squared, so we do keep that. And then plus 1. Again, this is definitely more annoying than the previous one, but let's see how this goes. So 2/3 minus, what will this be? 1/2 times 2 squared, so 1/2 times 4, that'll be minus 2 plus 2. So these cancel each other out, it looks like. So we get 2/3. And then what do we get over here? We get, that's a 0. So that's a 0. And then this will be 1 minus 1/2. So this will be plus 1/2. So this one is actually 2/3 minus 1/2. It looks like. So 2/3 minus 1/2. And then again, we could do a common denominator here of 6. So double that. So that'll be, I guess, 4/6. And then this one, to get 6, I'd have to multiply the top and bottom by 3. So 3/6. What is 4/6 minus 3/6? 1/6. So there you go. That's how you would integrate this with respect to y. And you can see that we get the same value as we did previously. And that's kind of the whole point. So there you go. That's kind of not an easy example by any means, but it's one of the easier or more straightforward versions of these problems. Believe it or not, it could get more complicated. But overall, this is a pretty straightforward version. Hopefully that makes sense. Just let me know if you have any questions. But yeah, that's a worked example of how you can find the area bounded between two curves, integrating with respect to x or y, whatever is more convenient. And you should get the same result in both cases. So there you go. Hopefully that makes sense. And just reach out if you have any other questions. Thank you.